Okay. In the last lecture, what we have seen is that for uniformly continuous semi group, okay, we have proved one particular theorem. So, let us look at that theorem. So, and then we have proved that theorem completely. So, the theorem statement is that a linear operator A is infinitesimal generator of a uniformly continuous semi group if and only if A is bounded linear operator. Okay. So, what does it mean? That if I have a bounded linear operator, then I can view this as infinitesimal generator of a uniformly continuous semi group. On the other hand, if A is identified as infinitesimal generator of a uniformly continuous semi group, then A is nothing but a bound linear operator. Okay. However, this theorem does not necessarily says how A and the generator and the semi group are associated. Okay. So, here if I have a bound linear operator, I can always define what is e to the power t A, okay, as limit of the series expansion of the exponential series. Okay. But this theorem does not say that the semi group what we are going to get from e to the power of t A, whether there is any other semi group also for which A would be the infinitesimal generator. Okay. It does not say that the generator uniquely determines the uniformly continuous semi group. Okay. Okay. I mean, of course, I mean if you have one uniformly continuous semi, if you have a semi group, you get a generator, that is okay. But given a generator, whether you can get a unique semi group, so that question is not addressed here. Okay. So, we are going to see one theorem today which really talks about that. So, this is the statement of the theorem. So, let you have two different uniformly continuous semi groups, okay, of bounded linear operators T t and S t. Okay. Now, this is the generator T t minus I by t limit t tends to 0, and that you say A, okay, and S t minus I divided by t and limit t tends to 0. So, that is A. So, this limit exists, correct, because it is uniformly continuous. Uniformly continuous semi group, for that we have seen that this limit exists, correct, and that limit would give me some operator, and that will be bound linear operator. Okay. So, imagine that you have two different uniformly continuous semi group, for them these limit values are same. Okay. Now, question is that can I conclude that the semi groups are same, T and S both are same. Okay. Basically, if you look at some any nonlinear functions, so some functions f and g, and you just have that its derivative at 0, okay, are matching. Okay. That does not necessarily mean that the function will be the same, correct. However, if they are linear functions, okay, and their slopes are matching and both starting from 0, okay, they are the same thing. Okay. So, now here for semi group, how to do this? Okay. So, that is the question. Okay. So, this is like derivative at 0. Okay. Okay. So, the implication of this theorem is the following. So, it says that a bound linear operator A generates a unique uniformly continuous semi group. Okay. Because if A is generator of two different semi groups, they are essentially the same. So, the A uniquely determines the semi group. Okay. So, T t, let T t be a uniformly continuous semi group of bounded linear operator. Okay. So, then there exists a bound linear operator A such that T t can be written as e to the power of t A. That is also a consequence of this theorem. Why is it so? Because I mean in earlier theorem we just proved that if I have a uniformly continuous semi group, then it has a its inference generator is boundary linear operator, and then from that boundary linear operator I could define e to the power of t a, but this e to the t a would be a semigroup, and this t t which we started with is also a semigroup. Why should they be same? Because for both the inference generator is a, is the same. Okay. So, this is also a consequence of this theorem, that every uniformly continuous semigroup of boundary linear operators can be written as e to the power of t a for some boundary linear operator a. Okay. Okay. So, this is one definition. I mean, this we have already seen the definition of C0 semigroup. So, here this is just defining what is strongly continuous. Okay. If T is a C0 semigroup of boundary linear operators on X, then T is called strongly continuous. Okay. So, because we have used the word uniformly continuous. Okay. There what did you get? That the limit t tends to 0, t of t minus identity, that norm goes to 0, correct. So, t t converges to identity in the operator norm. However, here we have fixed some x small x in the Banach space, and then the action of the operator on small x, then that would give me a a vector in capital X, correct, a member in the Banach space, and that member is a function of t. As t tends to 0, that member converges to x itself. Okay. So, this is like pointwise convergence, correct. It is like a pointwise convergence of t t to identity operator. Okay. So, now we go to the next theorem, that let T t be a C0 semigroup. Okay. So, then here we do not assume that T t is a, I mean capital T is a uniformly continuous semigroup. Okay. So, for uniformly continuous semigroup, we got a characterization. We got very clearly that this is nothing but e to the power of t times a. Okay, for some a, and that a would be the inferenceable generator, and that a would also be a boundary linear operator. However, here when we choose a t from a larger class, is just a C0 semigroup, then can I say something similar? Okay. Of course, that particular statement is false here, but one can get something similar. What similar things? That let T t be a C0 semigroup, there exists some omega non-negative and some capital M greater or equals to 1, such that norm of T t is less than or equals to m times e to the power of omega t. So, like exponential expression, okay, the e to the power of t a kind of things, of course, we cannot get for this general type of semigroups. However, the norm of that operator, for norm of the operator can be dominated by some exponential map. Okay. For many proofs, actually this is really helpful. Okay. So, I have a semigroup. So, see semigroups definition clearly says like t of t composition t of s is equal to t of t plus s, correct. So, like exponent e to the power of t times e to the power s is e to the t plus s. Okay. So, like the property itself is there for exponential functions. Okay. So, it is very natural to expect that this growth, as time goes to infinity, its growth is like exponential, it is very natural, but it is not obvious, correct. It is natural to anticipate, but it is not obvious. So, this theorem says that indeed one can do that. So, like as t belongs to closer to infinity, so its growth can be upper bounded by an exponential map. Okay. So, the proof is not very difficult. So, it is it just uses one particular theorem of functional analysis, that is boundedness, uniform boundedness principle of family of boundary linear operators. Okay. So, we start this proof here. So, we know that since TT is from C0 semigroup, we know that if I choose a sequence Tn which converges to 0, okay, then Ttn of x converges to identity operator of x, basically Ttn x converges to x, right, because it is C0 semigroup, correct. So, as Tn goes to 0, Ttn goes to T of 0 x, right, Ttn of x goes to T of 0 x, T of 0 is identity. Okay. So, for each x we have this. Okay. So, this is same as saying that we have a family of operators. Okay. So, that I mean for every n we have an operator. Okay. So, this family of operators, they converge pointwise to another operator, identity operator, correct. Okay. So, pointwise as n tends to infinity. Now, from there we get that since this is converging, so this if I put x, so this is a converging sequence. So, a converging sequence is of course a bounded sequence. So, if I take supremum for all possible n, Ttn x is finite for each x. Okay, this is finite for each x. So, that we get. So, that is also one sufficient, I mean in the sufficient conditions for applying uniform boundedness principle of for a family of operators, we need that pointwise boundedness, correct. So, for every point x, okay, this family this this application of these operators, okay, that is finite. So, now since this is true, so we can apply uniform boundedness theorem, okay, from functional analysis course, and then what we get is that from this pointwise boundedness to the uniform boundedness. Okay. So, like supremum over all possible n, and then there we can take the operator norm. Okay. So, instead of the pointwise here, so I am taking operator norm here. So, norm of Ttn supremum over all possible n, that is finite. Okay. So, this is first thing we obtain here. So, next what we do? We assume if possible, actually this is wrong thing, but we are going to show that is wrong. Okay. So, assume, so this is like proof by contradiction. Assume if possible that supremum of T of t is infinity for, I mean when we take supremum small t from close 0 to eta for any positive eta. So, let me put it in a different phrase. You fix one eta positive, and then you get an interval 0 to eta, and then on that interval you take this function T of t norm. So, norm of T of t, that is a non-negative function. Okay. So, and then you take supremum of this function. Okay. The supremum of this function on this interval 0 to eta. Assume if possible that is infinity, no matter what eta you choose. Okay. Okay. So, assume that if possible that is true. Okay. So, then what we do is that using this fact we should get a contradiction. So, I mean, so what we do is that because here supremum over all possible t, it is not directly saying that we are getting contradiction, we have to do little more work. Okay, we have to actually consider a sequence decreasing to 0 because Tn converges to 0. Okay. So, this way. So, we do this is a very elementary argument. Then consider a sequence 1 over n converges to 0 as supremum 0 to 1 over n T of t, this is infinity because of this assumption, because eta could be any positive. So, 1 over n is also positive number. So, 0 to 1 over n on that supremum if I take of Tt, that would also be infinity due to this assumption. So, I can always find one Tn in this interval such that Ttn would be more than or equals to n. I can always do this. Why? Because here in this supremum on this is infinity. Okay. So, that means for some t is becoming very large and arbitrarily large, whatever large number n is, I can always find one t n in this interval such that for which the norm of t t n would be more than or equal to n. So, if you cannot do this, then actually this is wrong, correct. So, if we assume this, then of course, we will be able to find out such t n. When we fix t n, then we take instead of n plus 1. So, 0 to 1 over n plus 1 even a shorter interval, but that 1 over n then 1 over n plus 1 you consider that is eta, again use the same argument, and you consider again another t n plus 1 between 0 to eta or 0 to 1 over n plus 1, such that again you get. So, you generate such type of sequence of t n, okay, for which norm of t t n is increasingly larger, okay, more than n etc. And then the choice of t n is such that it should go to 0. Why? Because t n is always between 0 to 1 over n, and as n tends to infinity, this thing goes to 0. So, t n is by construction converges to 0, okay, as n tends to infinity. On the other hand, t t n, okay, by its construction it is going to infinity. Okay. So, here we get a contradiction therefore. Okay. So, it implies that supreme for all t t n is infinity, but here we have second supreme for all n, t t n is finite. Okay. So, this thing is contradicted due to this assumption. So, this assumption is wrong. Since this assumption is wrong, so what we can assure is that at least there exists some eta positive such that the supremum is finite. Get the point? Okay. That we do. Thus, there exists some eta positive such that supremum over 0 to eta in this interval norm of t t is finite. We call that number as capital M. Okay. We call this number as capital M. Now, as t of 0 is equal to 1 and we are taking supremum. So, t of norm of t 0 is 1 and this is a member, and we are taking supremum over all possibilities. So, m would be at least 1, it will be 1 or more than 1. Okay. So, here we get existence of such m and also that it would be not less than 1. Okay. Good. So, now we have to cook up omega. See, I mean recall the statement of the theorem, we have to come up with existence of omega and m. So, we got a candidate m there. Now, we are going to cook up one omega. So, we define omega to be log of capital M divided by eta, okay. Which eta? This eta, okay, this eta, log of capital M divided by eta. So, this is of course greater or equals to 0 because eta is positive, m is 1 or more than 1. So, it cannot be negative. So, omega is non-negative. Okay. Now, if we define omega this way and we calculate e to the power of omega, so e to the power of eta times omega, e to the eta times omega is capital M, correct, capital M, and then we take power of by t by eta both sides. So, e to the power of eta omega becomes e to the power of t omega, and right hand side will be m to the power of t by eta. Okay. So, we get this nice relation between m, eta and omega. Okay. So, omega is defined this way. So, that means this thing. Okay. So, now we consider an arbitrary small t. Okay. So, here see, I mean I could only assure that on the interval 0 to eta t of t is bounded. Okay. So, on that it is bounded. Okay. But for arbitrary t we need to get something, correct. It is exponential, is bounded by exponential growth, I mean dominated by exponential growth, that we need to come up with. And for that we of course would use the semigroup property of T t. Okay. So, for any small t positive, let n be such that t is equal to n times eta plus delta. Okay. So, like division algorithm, correct. So, like if so if small t is more than eta, if small t is less than eta, we do not need to worry much about it, because for this we already got. If small t is say more than 2 times eta, okay, but less than 3 times eta, so we write down that t is equal to 2 times eta plus delta, where delta is between 0 and eta. Okay. If small t is any number, okay, so we can actually divide small t by eta, okay, and then we take the floor function. Floor function means the largest smaller integer, okay, that would be n, correct, because t by eta, okay, so that would be so that is n. So, t is equal to n eta plus delta, where delta is between close 0 to open eta. Okay. We would be able to we would always be able to find out such n. So, now norm of t you should consider for this general t. So, this small t can be written as n eta plus delta. So, t of capital T of n eta plus delta is capital T of n eta times composition with capital T of delta. So, capital T of delta would be there and capital T of n times eta, but capital T times T of n times eta can be written as capital T of eta plus eta n times, and there again we use semigroup property. So, you get T of eta to the power of n. Okay. So, we write down norm of t is equal to norm of t delta times t of eta to the power of n. Since delta is between 0 and eta, so we know that t of delta is less than or equals to m. Okay. So, t of delta, so this norm of the product of operators is less than or equals to product of the norms. So, here for norm of t delta we are going to get one capital M, and from t of eta also we are going to get capital M to the power of n here. So, we are going to get m to the power of n plus 1. Okay. However, as I told that this this 1 if I take and then n, this n is what? N is the floor function of t by eta. Okay. So, I can write down that this is less than or equals to m times m to the power of t by eta. Okay. So, now this t by eta is here we see that m to the power t by eta is e to the power of t omega. Okay. So, we substitute that thing here. So, we get is equal to m times e to the power of t omega. So, norm of t can be written as less than or equals to m times e to the power t omega. So, that is the proof of this theorem. Okay. So, one comment that here when we have obtained this omega and capital M, so we they are independent of the choice of t, correct, because here of what we have obtained that there exists some eta such that okay, this supremum of whole thing is equal to m. So, this m is independent of choice of small t, okay, this small running t, and omega is constructed using eta and m. So, here this m and omega are not function of t. Okay. So, here as a function of t, okay, so these are constant, okay, and then e to the power of t. So, this is actually upper bounded by one exponential function. Okay. So, that is the proof of the theorem. Okay, thank you.